Hi, good morning, good afternoon, everyone. My name is Shivasai Bandugula. So, I am very much pleased to present you my final thesis, which is building question answering system using knowledge graph, especially in the medical domain. So, this research was as part of my master's program at Liverpool John Moores University under the guidance of Dr. Manisha Rajendra Dage, my thesis supervisor. Over the upcoming slides, I will be walking you through the background, methodology, results, and key contributions of my work. Over the past decade, there have been massive search in unstructured medical data, from patient health forums to electronic health records. People are frequently turning to digital platforms for health-related answers. Unfortunately, existing QA systems are general purpose and they lack the domain-specific reasoning needed to provide safe and reliable responses, especially in the medical context. Furthermore, medical knowledge is highly interconnected. Symptoms can map to multiple conditions, treatments, depending upon the individual cases, and terminology varies. This is where knowledge graphs comes into play. They will allow us to explicitly model relationships like causes treated by diagnosed with, which will enable the system to answer more complex queries. This research is motivated to bridge the gap between the raw unstructured text and structured explainable answers through semantic search and graph-based reasoning. Coming to the source of the data, we have used Hugging Face publicly available data set. This is a large data set which contains thousands of uh, question answer pair, medical question answer pair, so which will be useful for us in developing the QA system. Our goal was to build a knowledge graph using this particular data set. So we selected this data set, and coming to the use cases, this particular uh, thesis work especially helps patients and healthcare professionals. It helps patients who require quick and reliable answers for the medical queries, and it also helps the healthcare professionals uh, like who wants this structured representation of the medical entities and the relationships like uh, a disease it is caused by like a disease has particular symptoms and a disease can be treated with particular diagnostic procedure or it is treated by a particular specialist. So uh, this medical structured representation of these medical entities will be helpful for the healthcare professionals. And coming to the challenges of the existing approaches, uh, so natural language queries are often complex. Traditional models lack the reasoning abilities and cannot explain how the answers are derived. So our task is to build a medical question answering system that uses knowledge graph to bring structured semantic similarity to understand the queries and answer generation that is both accurate and explainable. The aim of this research is to create a medical QA system that isn't just intelligent but also explainable. We want users to understand not only the answer but how system arrived at it. To do this, we need to bring together knowledge graph and language models. The objectives outlined uh, each major steps. So first, we extract entities from the medical text like symptoms, diseases, treatments. Then we construct a knowledge graph to represent those relationships. With that in place, we train graph embeddings, which allow us to perform semantic reasoning. We also use sentence transformers to interpret the user queries and match them with the relevant entities from the graph. Using Neo4j, we then traverse related nodes to build the required answers. The system is thoroughly evaluated and finally deployed with a Streamlit interface integrated with CI/CD pipelines for a scalable execution. Coming to the limitations of the current QA systems, many question answering systems today work well for the general topics, but they still have several problems, especially when we try to use them in the medical field. First, they often can't grow easily or think through complex situations. These systems are usually trained once and don't easily adapt when the new medical information becomes available. They can't reason the things like human do, especially when answering multi-step or detailed questions. Second, most importantly, uh, systems don't understand the deep relationships between the medical terms. For example, they might not know how a symptom is related to disease or what treatment is usually connected to a condition. This makes it hard for them to give complete or helpful answers. Another big issue is the lack of accuracy and context. These systems might misunderstand medical terms or not handle things like not having a disease properly. In medical conversation, getting the meaning wrong is actually too risky. Also, they need a lot of data to work well, and such high quality medical data is very hard to find. Even after training, their answers are often hard to understand or trust because reasoning behind the answer isn't clear. Most importantly, they don't use structured medical graphs or ontologies, which could help the system understand how medical terms are connected. Without this, their answers may be incomplete or too general. Lastly, they don't perform very well when the question is very specific to a medical field. They might give the general answers but miss the important medical details. These are the reasons why we build a system that uses knowledge graph so that we can improve accuracy, understand relationships better, and provide clear, helpful answers in medical questions. One of the most promising directions in recent QA research is the use of knowledge graphs, especially in complex and high stake domains like medicine. So why use a knowledge graph in question answering system? Firstly, a knowledge graph structurally represents information. Medical concepts like uh, symptoms, conditions, diagnostic tests, treatments are encoded as nodes, and the relationships between them, like causes diagnosed by treated with, are encoded as edges or relationships. This allows machines to navigate medical knowledge the way human expert might reason about it. Secondly, knowledge graphs support semantic reasoning. They allow the system to understand indirect connections. For example, recognizing that persistent headaches and vision changes might be the symptoms of brain tumor, even if the exact phrase isn't present in the question. Another huge advantage is reduced reliance on large annotated datasets. Traditional deep learning models require thousands of labeled examples, which is not always feasible in medical QA. Knowledge graphs, once constructed, serves as reusable and interpretable and queryable knowledge stores. Also, they enable multi-hop reasoning, that is, answering complex queries that require traversing multiple relationships. For instance, which tests are recommended for conditions that cause seizures would require at least two relational hops in the graph. Unlike deep learning black boxes, knowledge graphs offer explainability. The system can trace its path through the graph, something crucial in healthcare to ensure transparency. Lastly, the graph can be enhanced using the standard ontologies like UMLs, improving both completeness and clinical accuracy. These capabilities make knowledge graphs a powerful foundation for building intelligent, reliable, and domain-aware QA systems. Let me walk you through the overall methodology we have adopted to build medical question answering system using knowledge graph. The entire pipeline is designed to be modular, allowing each component to operate independently while contributing to the overall QA experience. We first started with the data ingestion and pre-processing, where the raw data set is cleaned and structured. The next clinical step is biomedical entity recognition, which extracts the medical relevant entities like symptoms, diseases, treatments, and tests from both questions and answers. Following this, we move to the core of our system, knowledge graph construction. In this step, we connected the recognized entities, medical entities, using medically meaningful relationships and store them in the graph database, enabling structured query and reasoning. The fourth stage is embedding generation, which transforms the graph elements into numeric vectors so that we can compare and search efficiently using similarity measures. These embeddings are used in semantic search phase, where user queries are interpreted and linked to the most relevant entities in the graph using vector similarity. Once we find the relevant entity, we move to answer generation, where the graph is traversed to gather related concepts such as associated symptoms or recommended diagnostics. The final response is formulated. When we evaluate the system, both Yeah, when we extract the final response, we structure the answer in the required format and give it to the user. We also evaluated the system both quantitatively and qualitatively. This includes metrics for named entity recognition, semantic matching, and answer quality. Finally, the complete solution is deployed using a web interface backed by CI/CD pipeline, GitLab pipeline, ensuring reusability and reproducibility. This structured approach ensures that each step adds value while keeping the overall system transparent, scalable, and domain aware. Data ingestion and pre-processing. So this phase forms the foundation of our pipeline. Pre-processing ensures that the raw medical data is transformed into clean and structured format is suitable for the NLP tasks. We started by sourcing the data from the Hugging Face Medical QA dataset, which contains thousands of real-world medical entities and their corresponding answers. So the link of the dataset is provided, and these are often written in free form text and contain typographical errors, abbreviations, or inconsistent formatting. So the first step is pre-processing. In this pre-processing step is cleaning. We remove the unwanted punctuation, lowercase the text, and handle irregular spacing and symbols. This ensures consistency across all the inputs. Next, we tokenize the data, breaking down sentences into words and meaningful chunks. This is essential for our downstream task, which is named entity recognition (NER), where each token is evaluated for potential medical significance. We also removed the stop words, common words like the, is, and of, etc., so that do not contribute meaningfully to any medical interface. Additionally, we normalized the structure of the question answer pairs, handling contractions and medical shorthand to standardize the language. Finally, we generated an intermediate structured data set that preserves context while ensuring compatibility with NER models. This step was crucial for maintaining entity boundaries and improving tagging accuracy in the next phase. The output of this phase was cleaned, pre-processed dataset, one that is now ready for advanced processing like entity extraction and knowledge graph building. In this stage, we extracted the key medical concepts from the pre-processed questions and answers, which we have done in the previous stage. So, so that's why we named this stage as a biomedical named entity recognition or NER. So our goal here was to automatically identify entities like diseases, symptoms, drugs, diagnostic procedures, and etc. within the text. These entities form the building blocks for our knowledge graph. We experimented with several NER models. First, we tried Space's standard EN Core Web SM, but it wasn't trained on medical data, so its accuracy on medical text is very low. Next, we moved to size spaces models, specifically ENNER BC5CDR-MD and ENNER Bio NLP 13CGMD, which covers granular biomedical categories, which give better performance to compared to the above species models. But finally, we adapted to D4 data biomedical NER all, a transform model from the Hugging Face that merges the multiple biomedical datasets and can extract diverse medical entities with a strong accuracy. This model offered excellent performance for our domain and required minimal fine-tuning. It could correctly extract entities like MRI, even when like it is phrased in different ways. And yeah, the output of this particular stage is rich set of structured entities tagged with their types, forming the basis of the knowledge graph relationships in the next step. So as you can see in this picture. After extracting the entities, the next phase was constructing the knowledge graph, which is the core of our QA system. The idea here is to represent real-world medical knowledge in a structured, interconnected format, where each node is an entity and like a disease, symptom, or treatment, and each edge is a semantic relationship between those medical entities. For example, migraine may have a asymptom relationship to headache and may be connected to CT scan through a required test edge. So we built this graph using Neo4j, a popular graph database that supports the Cipher query language, which is excellent for querying complex relationships. Neo4j allows us to visualize and validate the graph interactively through Neo4j browser. To populate the graph, we used a rule-based engine to classify the relationships between the extracted entities. For example, if a treatment-related keyword like drug or medication was found near a disease, we created a recommended treatment relation. So similarly, when a word symptom or pain is found near the entity, it has like we created a has symptom relationship between the entities. So the node types were we defined include like diseases or disorders, symptoms, treatments, and diagnostic procedures. And the relationship includes like sign, symptom, diagnostic procedure, recommended treatment, etc. So this structured graph now acts as a knowledge backbone, allowing us to retrieve answers not through unstructured search, but through semantic explainable connections between the medical concepts. This design enhances interpretability and opens the door for graph traversal-based answering, which I will be explaining in the next stage. Once the knowledge graph is constructed, we needed a way to bridge the gap between the user input in natural language and graph's structured format. This is where embeddings and semantic search comes into play. We used PyKeen, a library specifically designed for knowledge graph embedding, to convert each triple from the graph, like relationship and tail format, into high-dimensional vectors using the Transy model. These vectors capture the semantics of the graph structure in a format that machine learning models can easily understand and compare. Each entity and relationship in our graph, like CT scan, is transformed into a vector. This now allows to compute similarities between the user input and graph nodes, not just exact text matches. For user queries, we employed the sentence transformer model, specifically all mini LM L6v2, which is lightweight yet powerful BERT variant. When a user types something like I feel dizzy or weak, the model embeds that into a dense vector. We then use face, a fast approximate nearest neighbor search library, to compare that query vector with all the entity vectors which are present in our knowledge graph. This retrieves the top k most similar entities. One major advantage of this semantic approach is flexibility. Even if the user says feeling disoriented, which may not directly match dizziness, but our model can still understand the contextual similarity between the user query and the embeddings which are present in the knowledge graph and return the right node. In short, this setup enables our QA system to move beyond the exact keyword matching and use the contextual embedding for the accurate and intelligent entity thinking. This makes our search both intelligent and explainable, forming a key link between the natural language input and structured medical language. In this phase, we focus on how the system processes the user queries and generates accurate answers using our knowledge graph. First, once the user submits the query, for example, I have frequent headaches and like what I need to do, the system transforms this sentence into dense embedding using sentence transformer model. This semantic embedding helps us to move beyond the keyword matching and truly understand the context of the query. Next, using Facebook AI similarity search, we compare this embedding to our pre-computed knowledge graph entity embeddings. This will allow us the system to identify the most semantic relevant entity. Let's say migraine in this case. With the matched entity, we use Neo4j to query the knowledge graph. We run cipher queries to extract all directly connected relationships like symptoms, diagnostic procedures, and recommended actions. These results are structured based on relationship type. For example, if migraine has links to MRA under diagnostic procedure and photophobia under symptoms, those are grouped and returned accordingly. The final output is presented through our Streamlit web interface. The UI not only displays grouped results but also displays scoring and accuracy count, occurrence count, giving users the clearer view of how strongly an answer is supported by data. This layered approach, semantic search followed by graph traversal, ensures contextual understanding, relevant entity mapping, and medically interpretable answers. This significantly improves over traditional keyword-based QA systems. Yeah, in this slide, we will be focusing on the evaluation of the entity recognition module in our system, which plays a foundational role in constructing the knowledge graph and enabling meaningful downstream reasoning. We use the biomedical NER model a transformer-based linear pipeline trained on variety of medical corp data to identify key medical entities such as symptoms, diseases, procedures, and treatments from the question answering dataset. To evaluate its performance, we adopted standard metrics. Precision, like how it measures how the predicted entities, how many of the predicted entities are actually correct, and recall, it measures how many of the actual entities are successfully identified. So F1 score is actually the harmonic mean of precision and recall. So this is here as you can see the performance metrics of each entity type we have used in our uh, like the most common entity types we have used, like symptom. For symptom, the precision is 88.3%, recall is 85.1%, and F1 score is 86.7%. So like this, for each entity we have calculated precision, recall, and selected the appropriate in-year model, which we finalize the appropriate in-year model, which we can use for the entity recognition. This step is basically performed uh, for the entity recognition step. So, and we also checked the knowledge graph quality, like we have using the Cipher queries, we uh, and Neo4j browser, we uh, graphed through the important medical data and just manually checked the relationships and entities are correct or not after the entity extraction and knowledge graph construction. In this slide, we evaluate how effectively our semantic search component retrieves the most relevant medical entity for given user query. As discussed, our system uses sentence transformers to convert both queries and entities into high-dimensional embeddings, and face is used to find the most similar vectors based on the cosine similarity. To evaluate this retrieval step, we used three important metrics: top Q accuracy. So this tells us whether the correct entity appears in the top K retrieved results. In our experiments, we found that with the top 5 accuracy, our system retrieves the correct entity around 94% of the time. This is particularly okay, 92% of the time. This is particularly important because user often expects the right solution for the first few results. Cosine similarity score. This is a numerical value that measures how close the query and entity vectors are. A higher score means a better semantic alignment. It varies from -1 to 1, like negative being the opposite direction, closeness in the opposite direction, and positive being the closeness in the uh, same positive direction. So our average cosine similarity score for correct matches was found around 0.85, which shows a strong relevance between the user query and the matched entity. Mean reciprocal rank. This metric tells us how high the correct entity appears in the ranked list. So we got 0.92. So this is the semantic search evaluation we have performed between the user query and the uh, entity matched entity in the graph embeddings. As shown in the figure, when the user inputs the query, I have a memory problem or something like that, the system processes it through the sentence transformer model, converts it to embedding vector, and performs semantic search using face. In this case, it maps the entity with the most relevant to the user query, which is brain. And once the closest matching entity is identified, the system queries the Neo4j based graph, knowledge graph for all the relevant relationships linked to brain. Then it categorizes and displays the associated uh, things, symptoms, or disease conditions, or diagnostic tests required. So it is fully explainable because each piece of information can be traced through the edge in the graph, like as symptom leads to or requires tests, etc. This interpretability is critical in the medical domain, where understanding how the answer is derived is just as important as the answer itself. Additionally, yeah, this UA is built using Streamlit. It's lightweight and responsive. So and it is capable of being deployed in the cloud or can be used locally for demonstration. As we come to the end of this project, Let's recap what we have achieved. Our work successfully demonstrated how knowledge graphs can be used to build the interpretable, accurate, and scalable medical question answering system. By combining structured relationships with semantic understanding from transformers, we have built a solution that not only answers queries but also explain the reasoning behind them. The potential applications are vast. In hospitals or clinics, this system can be integrated into design support tools for faster diagnosis. Patients can use it for self-assessment or understanding symptoms before seeing a doctor. Medical students or trainees can benefit from interacting with a visual or curable knowledge base. Looking forward, several exciting directions remain. First, incorporating temporal reasoning will allow us to manage time-sensitive data such as treatments across stages or stages that evolve. And second, integrating with external biomedical ontologies like UMLs will enhance our entity classification and standardization, making the system interoperable. Lastly, adding multilingual capability and coupling with large language models can enhance answer fluency and accessibility for global users. This project provides a strong foundation for future exploration in trustworthy and interpretable medical AI systems. Finally, thank you everyone. And I would also like to thank my thesis supervisor, Manisha Dage, for constant support throughout my thesis work. Thank